let's see how you're doing on these so far. So what's the first step when trying to find the effective rate for compound interest? First thing we need to find is future value. And we need to use that to find the amount of interest, right? Our future value here is going to be our principal of $8,000 times 1 plus what goes in here? 0.10, 10%, divided by what? Compounded quarterly, so divided by 4, to the power of, why is it not 12 here? For compound interest, we only always go 1 year max. If it's more than a year, we only go for 1 year. How many did I catch with that? A couple of you? You don't have to admit to it. It's okay. Yes, if our period is more than a year, if we're doing effective rate, we only go for 1 year. So 8,000 times, parentheses, 1, times, parentheses, 1 plus 0.1 divided by 4 to the power of 4. $8,830.50. So then we use that, we're going to subtract our principal of 8,000 to get $830.50 is our interest. So then we bring that back to step 2, which is to go back into I equals PRT. So the interest is $830.50. Our principal is 8,000. We're looking for a rate, and our time is 1 year. So we're going to divide 8,000 divided by 1 is just 8,000. So I'm just going to divide by 8,000. So $830.50 divided by 8,000. 0.1038125. That is equal to our rate. I didn't tell you where to round it, but we've been rounding to 100th of a percent unless we're told otherwise. So that's 10.38% is the effective rate. Anybody get that? Not really. I'm a little worried.
Is it only for quarterly that you do the 1 year, or is it for any annual?
Anytime it's over a year, you go for 1 year if you're doing effective rate.
Okay, but not for...
If you're doing future value, you still have to go all the way if you're just finding the future value.
Okay.
But for the effective rate, yes, if it goes past a year, you only do the future value for 1 year. So now for this one, we don't have to worry about it because it's less than a year. If it's less than a year, we go for the actual amount of time. So to find our future value here, this will be the $15,000 times 1 plus 0.08 divided by compounded monthly, so divided by 12. Did anybody put 9 in there? That's good. Every year there's a few people that get stuck on that. Even though we're only going for 9 months, it is still 12 periods, 12 months in a year. So we divide by 12 there. Now the power is going to be only 9 months, because that's how many periods we have. Should be just 9. The 9/12ths will mess it up. That'd be if you were trying to go for a full year simple interest, or for 9/12ths of a year simple interest.
Okay.
Yeah, if you're doing simple interest, you'd have to do the 9/12 as your time.
Okay, in one of my examples it says find the effective rate for 6% compounded monthly for 4 months.
Yep.
And then we did the 4 with 12 in that one.
Oh, what we did there,
Sorry, I did this one.
no, you're okay. We did 9/12 of a year. That's the time, times 12 periods in a year, and the 12s cancel out to just 9 periods. So that's what we did. It was compounded monthly, so it's 12 is the N, times our time was 4/12, so 12 times 4/12 gives us 4 periods. So that's what you're thinking there. So we get $15,924.38. These are our future value. So the interest amount is found by subtracting the 15,000. So $924.38 in interest. So to find the effective rate, sometimes called the APY, annual percentage yield, $924.38 equals 15,000 times our rate. Now this is going to be 9/12. It's 9/12 of a year. 9 months out of 12 in a year. But you got to remember, way back when they figured all this stuff out, they didn't have television. So they had a lot more free time. So anyway, we have to combine the 15 and the 9/12. So 15,000 times 9/12 is 11,250 times R, and we have to divide by 11,250. So 924.38 divided by, I'm just going to use the previous answer, 0.8 or 0.0821671. So moving my decimal point makes that 8.22%. Is our effective rate. Anybody get 8.22? We got a couple at least that time. Cool. I'm a little happier now. Are you happy that nobody got? What am I, a monster? I feel a little sad now. I'm going to ask to interject a question here. Can we just subtract the $2,000 to get the interest? No, why not? That's for 8 years. For effective rate, we can only go 1 year. So we have to find a new future value. 2,000 times 1 plus 0.07 divided by 12 to the power of 12. Which is 2144.58. That's the future value we have to use. Give you guys a minute or so to go through it. I realize some of you are still working, but see if you can stay ahead of me. Subtract the 2,000 principal to get 144.58 interest. So it's 144.58 equals 2,000 times R times 1. So it's just 144.58 divided by 2,000. 0.07229 is our rate. So that is 7.23%. Did we get that? Good deal. We're getting a little better. How many of you caught that it had to be adjusted for 1 year on your own before I said anything? Okay. That is a big thing when you're doing effective rate. Make sure you don't go over 1 year. Okay, tonight we are going to talk about something totally different now. We're going to talk about annuities. And the difference about an annuity 1, T, or 2. We're going to go with 1. What the heck? No. The thing with annuities is your calculator can do the whole thing. It's all just getting the right formula. And there are 4 formulas, but it's really only 2 formulas with different variations. The thing with it, the difference about an annuity is we are not just starting with a single value. Up here with our future and present value, there was just one amount, and we let it grow into one other amount. In an annuity, we have our timeline here. We're going to have a future value, but we're making regular payments that are evenly spread out through that whole timeline up until the end. So we're not getting one lump sum, we're getting small payments every regular period over time, which is a lot more realistic, because how many of us have, a few $1,000s just thrown all at once? It's easier to take out 100 or 200 every paycheck or whatever and have it add up. There's some vocabulary we need to talk about. In an annuity, we have future value and we do have present value, but the present value and future value don't work together. So we have something called the accumulation phase of an annuity. In the accumulation phase, you start with 0, with nothing. Make regular payments. And of course, you earn interest on those payments. Get to an ending lump sum. Yeah. It's just assumed you're earning interest on all this, but yeah, you earn interest on your payments after you're paying them in. Yep. I put ending lump sum. So you end up with an ending lump sum. There are 2 types of annuity during the accumulation phase. There's an ordinary annuity. In an ordinary annuity, you pay in at the end of the period. Anybody here an accounting major? Okay. When you talk about in accounting, and when you get into intermediate accounting, they'll talk about annuities. And so they'll say the annuity starts on this date. Well, maybe they'll say December 31st, 2016. The first payment is made on December 31st, 2017. That means it's an ordinary annuity. They're making the payment at the end of the next year. If they say that the annuity starts at December 31st, 2016, and the payment is made, the first payment is made either December 31st, 2016 or January 1st, 2017, they're making the payment at the beginning of the period. And that's what is called an annuity due. You pay in at the beginning of each period. All of the tables in our book are for an ordinary annuity. The formulas I'm going to give you are for an ordinary annuity. An annuity due uses the tables and the formula with an adjustment factor. All that adjustment factor is figuring in the interest for an extra period. Because since you made the payment at the beginning of the period, it sits there for one period longer and gains that much more interest. So an annuity due with the same payment amount, if everything else is the same, the amount of your payment, the interest rate, the frequency of your payments and everything is the same. An annuity due will always have a larger ending balance, a larger future value. So an annuity due, you get more interest because you get another compounding period in it. Then there's the liquidation phase of the annuity. This is where you are drawing money out. You start with a lump sum, a large amount of money sitting there. Take out or draw out regular payments. Could be once a month, could be once a year, could be once a quarter, could be once a week. The ending balance should be zero. So in the accumulation phase, we started out with zero, made these regular payments to get to a lump sum. In the liquidation phase, we start out with a lump sum and we draw them out to get to zero. Fortunately, in the liquidation phase, there is no ordinary versus annuity due. In the liquidation phase, it's always assumed that you're drawing it out at the end of the period. So you don't have to separate it out. To figure out the amount of a loan payment, they use the liquidation phase formulas. So we will actually look at that, using the liquidation phase formulas to figure out what your payment amount will be on a loan. That won't come until next week. So this week, we are going to focus on the accumulation phase. So I'm going to ask, how many of you have calculators that are a one-line display? So if you look at the screen of your calculator, there's only what you type in when you hit equals, what you typed in disappears and you can't see it anymore. Okay. Yours is a 2-line display. You're good. If you have the 1-line display, because yours, once it equals, the answer appears, but what you typed in goes up on the top of the screen, or stays on the top of the screen, yeah. So you can still see what you had typed in. With these formulas we're going to do, the 1-line display calculator has a character limit. There's only so many characters you can put in before you hit enter, or it's going to cause an error. It won't handle it. So these formulas, these next 2 weeks, there are going to be some formulas where the 1-line display calculator cannot handle it. So you have 2 choices. One is you can spend the $13 to get the 2-line display calculator, or let me know and I will show you how to break the formulas down into 2 steps. So you'll have to do half the formula, get an answer, and then do the other half of the formula. There also will be tables in the book that do these as well, but as we've seen before, that there are certain interest rates that the tables don't work for. Tables don't work for, put it that way. Okay, so the accumulation phase. What we're going to start out with now is making regular payments. Figure out what the ending amount will be. So we're going to find the ending amount. That ending amount is the future value. The future value is the amount of that payment times, make sure you write small, leave yourself a lot of room here. Yes, there are 3 open parentheses. The first part of this will look fairly familiar. 1 plus R divided by N, close parentheses, the power of N times T, where T is your time again, minus 1, close parentheses, divide by, open parentheses, R divided by N, close parentheses, and close parentheses. Doesn't that one look like fun? Totally. Now I'm going to pause here for a second. I want everybody to just double check what I have written here and what you have written in your notes. There's a lot of stuff there. The parentheses are a lot of parentheses. Just make sure it's exactly the same as what it is up here.
You don't have to really put that time in front of those parentheses.
Most of your calculators you don't. I always do just to be safe, because there are some, the 1-line display calculator you do have to.
But these ones you don't, right?
Those you should be okay. Type in for me right now 8 times, or just put 8, open parentheses, 3 plus 1, close parentheses, then hit equals. Does it give you 32? Okay, then you're good with that one. So you don't necessarily have to have the times. One of the reasons I put the times in there is when we're going the other direction, you're going to put divide in there. So everybody's got their formula good? So let's do one example and then hit our break. So let's say you are going to invest $50 a month at 6% interest for, we got a lot of people in here that are in their 20s. So let's go for 40 years. It'll be 40 years before you retire. Find your future value. So the future value is going to equal 50 times 1, 2, 3. 1 plus what goes in for R, 0.06, divided by what goes in for n. Well, it doesn't tell us what it's compounded, but it's implied. We're paying in $50 a month. So that implies we're compounding the interest every month. So divided by 12. Close parentheses to the power of, perfect, 12 times 40, minus 1, close parentheses, divided by, open parentheses, 0.06, divided by 12. Close and close. Now again, just because it's easier for me for some reason, I'm going to cross off the 12 times 40 and put in 480 there. So on my calculator, 50 times 1, 2, 3. This is another spot where having the 2-line display helps, because on the 1-line display, it's hard to tell whether you hit it 3 times or not. 1 plus 0.06 divided by 12, close parentheses. Now I'm going to have you pay attention to me here for a second. To the power of 480. Some of your calculators will work like mine here. Notice after I type in the 480, the cursor is still up there in the power. I have to either hit the right arrow or the down arrow to get out of the exponent. If you don't do that, it's going to put the rest of the formula up in that power, and it's going to really mess things up. So now that I'm out of there, I hit minus 1. That's my next step in the formula. Close parentheses. Divided by, open parentheses, 0.06 divided by 12. Close and close. We would end up $50 a month for the next 40 years at only 6% interest. It would be $99,574.54. So only $50 a month would give you $100,000 in retirement. That's only 6% interest. What if you do that a little smarter and get 10%? So I changed my percent to 0.1 instead of 0.06. That now jumps up to 316,000. It triples it. More than triples it. So those of you that think, even a half a percentage point or whatever on your investments isn't a big deal, it is huge when you're looking at 30 or 40 years down the road. Okay, it is time for our break, so let's do that. We'll take our break here, and we'll come back at 6:31.